Okay, this worksheet here is where section 4.6 would begin. The topic is rational functions. Definition: a rational function is a function of the form f of x equal p of x over q of x, where p of x and q of x are polynomials. And just like with numbers, you can't divide by 0. When we graph a rational function, we have to consider any asymptotes that would be on the graph. An asymptote is a boundary that the graph will approach, but it will never get there. There are three kinds of asymptotes. There's a vertical asymptote, a horizontal asymptote, or an oblique asymptote. An oblique asymptote is one that has a slant to it. I've got the information for how to find the asymptotes on a graph. So to find a vertical asymptote, you're going to first make sure that the function is in lowest terms, and the function will have a vertical asymptote at the equation x equal k if k is a real zero of the denominator q of x. We'll be able to get the equations of the asymptotes right away just by simply knowing the domain of the function. Any numbers that we throw away as a result of the domain are going to create vertical asymptotes on the graph. To get the horizontal or oblique asymptotes, you're going to use one of these three items here. You're comparing the degree of the top to the degree of the bottom. Now remember, the degree is the largest power of x that we see. So if the degree of the top is less than the degree of the bottom, then y equals 0 is a horizontal asymptote. That will always happen. Item 2, if the degree of the top equals the degree of the bottom, you're going to have a horizontal asymptote, but it's not going to be at y equals 0. It'll be at y equals some other number, and you'll calculate that number through division, and you'll disregard the remainder that comes up. Item 3, if the degree of the top is 1 more than the degree of the bottom, then you're going to have an oblique asymptote, and to find the equation of that slanted boundary there, you're going to again use division and disregard the remainder. There's two options that are presented here for graphing a rational function. One of them, we've already kind of been there and done that before with transformations. So here's the graphs of y equal 1 over x and y equal 1 over x squared. We're first just going to answer some basic information about each one of these functions. So with y equal 1 over x, the domain is all real numbers except for 0. We know we can't divide by 0. And x can't be 0. There's no other number that's going to return 0, so y cannot be 0 either. What that means to us is that this curve is going to be approaching the two axes, but it's never going to get there, okay, because x can't be 0 and y can't be 0. Therefore, we're going to have a vertical asymptote at x equals 0. We use a dotted line to represent an asymptote, okay? And we're also going to have a horizontal asymptote at y equals 0. Again, we would represent that by making a dotted line here. Okay? So the curve is going to approach these two boundaries, but it's never going to get there. Because that would happen, there's no intercepts on the graph, okay, and we've already stated the asymptotes. This would be an odd function because, remember, an odd function is always symmetric to the origin. Any point that's on the graph, the negative of that point would also be there. Okay, so like if the point xy is on the graph, negative x, negative y would also be there. Here's 1, 1 is on the graph, negative 1 is also there. And here's another graph. We have y equal 1 over x squared, and again, we're just going to answer the basic information here. The domain, all real numbers except for 0. Again, we can't divide by 0 here. There's no other number that's going to return 0. Also, the fact that we're squaring x means that we'll never have a negative come out of the calculation. Therefore, y is going to be strictly greater than 0. So x can't be 0, we said. Therefore, there's going to be a vertical asymptote at x equals 0. Also, y can't be 0 either. And so there's going to be a horizontal asymptote at y equals 0. Again, represent the boundaries by using dotted lines there. Okay, so the curve is going to be approaching these boundaries, but it will never get there. Again, there's going to be no intercepts because the curve will never cross or touch the coordinate axes. This would be an even function because it's symmetric to the y-axis. Okay, so then on the next page, problem 1, they want us to graph the function g of x by using transformations on y equal 1 over x. I've already graphed y equal 1 over x again. We just looked at that on the previous page. And using what we know about transformations, we're going to, looks like we're going to shift this graph twice. We're going to go to the right 2 units because of the -2, and we're going to go up 1 unit. So all these points, bump them over to the right 2 and then up 1. All these points on the original are going to be relocated. Also, the asymptotes are going to be relocated. Okay, if you take the vertical asymptote and shift to the right 2, bumping up 1 doesn't matter, doesn't change anything, but you're going to have a vertical asymptote at x equal 2 then. And again, use a dotted line to represent that. The horizontal asymptote, when you go to the right 2, that's not going to change anything, but then when you bump that up 1 unit, you're going to have a horizontal asymptote now at y equal 1. So here would be the new graph. Problem 2 is a similar deal. We're going to graph this function using transformations on y equal 1 over x squared. Here's the graph of y equal 1 over x squared that we've already looked at on the previous page. The -1 in the numerator means that we're going to have a reflection about the x-axis, so this graph is going to be flipped upside down. And then the +1 that we see here means that we're going to shift to the left 1 unit. Okay, so when you do those two things, all these points are going to move, reflect about x, and then go to the left 1. Also, the boundaries are going to move also. The vertical asymptote, when you reflect about x, that's not going to change anything, but then when you shift to the left 1, you're going to have the vertical asymptote at x equal -1. And the horizontal asymptote, when you reflect about x and then shift to the left 1, that's not going to change the fact that you still have a horizontal asymptote right on the x-axis there, right at y equals 0. Okay, I feel like transformations are something that we've already been there and done that before. That's not really a new thing. It would hardly ever be the case that you would be all set up in just a convenient form to use transformations on a rational function. So I feel like the next thing is going to be kind of the more important option for graphing a rational function, and that's just using a list of steps here. Step 1, we're going to state the domain of f. Step 2, we're going to write the equations of the vertical asymptotes. We'll be able to get those immediately just by simply stating the domain. And again, we want to make sure that the function is in lowest terms before we state the equations of the asymptotes. That's going to be important for another problem that's later in this worksheet here. Step 3, write the equation of the horizontal or oblique asymptote for f. It will have one or the other, not both. So that's step 3. Step 4, determine the points, if there are any, where the graph of f will intersect the horizontal or oblique asymptote. Okay, I think at this point I should be more clear on the idea of an asymptote. An asymptote, I said earlier that an asymptote is a boundary where the graph approaches, but it's never going to get there. That's not really completely true. A graph can cross an asymptote. That will sometimes happen. The whole idea with an asymptote is that once you start heading out towards infinity or negative infinity, you're not all of a sudden just going to jump over the asymptote here and cross it at some random spot. Or if you did, we'd have that information known from step 4. Step 5, we want to determine the intercepts for f, and then step 6, we're going to graph, and we will likely need to gather up more points so that we have an accurate picture at the end. Okay, so here's problem 3. We're going to graph the function f of x. Step 1, the domain is all real numbers except for 3. I'm throwing away 3 since I can't divide by 0. Because I'm throwing away 3, I am going to have a vertical asymptote at x equal 3. And step 3 now is to get the equation of the horizontal asymptote. When I compare the degree of the top to the degree of the bottom, I have a degree 1 polynomial divided by a degree 1 polynomial. And so I'm going to have a horizontal asymptote. It's not going to be at y equals 0. It's going to be at y equals some other number that I'm going to have to find through division. So I've got my division set up here, and I've went through that division process. Now, after you've gone through the division process, you are supposed to disregard the remainder and then write as an equation y equals whatever information is to the left of the leftover there. So y equal 2 would be my equation of the horizontal asymptote. Step 4, I want to determine if the function crosses the asymptote. The way to figure that out is to set the function and the asymptote equal to each other. And so I've done that, set up my equation here. And when I solve this for x, I end up getting 1 equal negative 6. Of course, that's not true, but x was eliminated completely in this. So there's going to be no solutions to this equation. Therefore, there's not going to be any point where the graph is going to cross the asymptote. So that's good. We don't have to worry about that. Step 5, we want to get the intercepts. When you set the function equal to 0 and solve to get the x-intercepts, you're going to get x equal negative 1/2. To get the y-intercepts, you let x be 0. When you plug 0 into the function, you get negative 1/3. And so these 2 points would be the only 2 points I guess I know on the graph. So that doesn't really tell me a whole lot, although I do know some other information about this picture, the asymptotes and that. So I've got the vertical asymptote here, x equal 3, drawn. Also the horizontal asymptote, y equal 2, drawn. And at this point, I'd want to gather up some more points. Step 6, this is plot more points as needed in order to sketch the complete graph. You just get enough so that you can see the complete story of what's going on there. If I were to let x be, let's see, 2, and I plug that into the function, I would get negative 5 in return. So here's the point 2, negative 5 on the graph. If I were to let x be negative 2, that should be a negative there, plug that in, I get 3/5, and so here's another point. Now, these points here, along with the asymptotes being located where they are, kind of tell me that this graph has to be coming along below the horizontal asymptote. It's going to be passing through these points and then approach the vertical asymptote. The graph has to flow with the boundaries. Be sure to keep that in mind. That's why they're there. And so the left side of the graph is already set now. Okay, and then I'd want to get the right side figured out also. When I plug 4 into the function, I get 9 in return. When I plug 5 into the function, I get 11/2 in return. And when I plug 6 into the function, I get 13/3 in return. So I've plotted those 3 points. All 3 of those points are in the upper right-hand region of this graph, so that tells me that the rest of the graph is going to be in the upper right-hand region. And again, the graph has to flow with these boundaries here. That's why they're there. And so the graph is going to be coming down the vertical asymptote on the right, and it's going to be pulling away from that slightly, passing through these points, and then it's going to be approaching the horizontal asymptote from above it. Again, with the understanding that it's never going to get there, though. Okay, so that would be just a quick sketch of the graph of this function.